Okay, so last week we learned how to use our first derivative to determine things like where our function was increasing versus where it was decreasing, and to identify our relative maxes and our relative mins. So this video is going to cover how we use the second derivative to maybe simplify that process for maxes and mins, and then how we use the second derivative to determine things like what we call concavity of the graph, and then of course points of inflection. Okay, so the target for today is students will use the second derivative test to classify relative extrema of a function and determine concavity using the rules of derivatives to find the characteristic of a function. Okay, so with our first derivative test, we used the first derivative, we did our number line chart, things like that, figured out where it was increasing and decreasing, and then looked at where that change was. And if it was increasing and then it changed to decreasing, we knew we had a maximum there, versus decreasing to increasing, we knew we had a minimum. Now that test is great if I'm looking for maxes and mins, increasing and decreasing, because it kind of gives me those four characteristics in one. But if I'm just looking for a max or a min, I can actually use my second derivative to actually do that. And it's called the second derivative test. And the second derivative test says if we have a function that has a second derivative, if it exists on an open interval containing a value, that c value is going to be our critical value. If, of course, we get a critical value and we plug it into our first derivative, it's going to equal 0. And then if we take that value and plug it into our second derivative, if our second derivative is greater than 0, meaning that it's positive, let me grab a pen. So if our second derivative is positive, that actually means we have a minimum. Okay, if we plug it into our second derivative and it's negative, less than 0, remember that's just a fancy way to say something's negative, then we have a maximum. If we think about a graph, and we kind of started talking about this on Friday, let's say we had a graph, and this graph was not our function, but it was the first derivative graph. Okay. The zeros at which we see our function, or our first derivative, these zeros right here are x-intercepts. Those are our derivative equal to 0. So our derivative equal to 0. So those are our critical values. Now, if we look at the very first one on the left, that one right there, we see that our derivative is going negative to positive. So we have a maximum there. Sorry, not a maximum, a minimum. Excuse me, let me undo that. That would be classified as a minimum right there, because we went from negative y values to positive y values, when our derivative being negative to positive. At the second one, this would be our maximum, because we have a positive to negative. And then of course the last one would be again a minimum, negative to positive. So that justification. But if we bring in our second derivative is actually the slope of the first derivative of this graph that we see here. In order for us to go from negative to positive, we have to be going up. We have to be increasing, which is why if our second derivative is negative, right here, sorry, we'd have to be going up, our derivative would have to be positive. I don't know what I'm saying. If our derivative is positive, that means we have that minimum, and we can see that on the graph. On the maximum, we have to be going from positive to negative, so we have to be decreasing there, which means our derivative is, or our second derivative here is going to be negative, which is why we get a maximum. So because we're really quick at our derivative process now, it's actually a little bit more time efficient to use the second derivative test if we're only looking for maxes and mins. If I'm looking, of course, for increasing and decreasing and max and mins, I'm always going to go the first derivative test for that. However, if, and this is why we need the first derivative test, because of 3. If we get a critical value and we plug it in and our second derivative is equal to 0, that means our second derivative test fails and we have to go back to using our first derivative test. We wouldn't be able to use a second derivative test in that case. Okay, so let's kind of look at an example and what that means for the practice of this, or how we actually do this. in real time. So let's look at an example. It says the function we're given right there, it says use a second derivative test to find whether f has a local maximum or a local minimum at x equals -3, and then to justify your answer. So we're only looking at x is equal to -3. So there's first two things we have to see. We have to look at what is our derivative at -3? Is it, question mark, is it equal to 0? Because if it's not equal to 0, it can't be classified as a max or min. And then I want to look at the sign of that. Okay, so that's really what I want to look at. Okay, I want to plug it in and figure out what that value is and use our second derivative test to do that. So the first thing I need to do is get our first derivative, our f prime. And if I get that, I get 2x squared plus x minus 15. Right there, that's my first derivative. If I take my first derivative and plug it into -3, I'm looking to see, is this a critical value? So let's plug it in. Let's kind of calculate what that is. We get 18 minus 3 minus 15, which in fact is equal to 0. So that's a good thing for us because we have a critical value at x is equal to -3. So that's our first step, is this a critical value? That next thing we want to do is to take our second derivative. Let's find our second derivative. Remember, that's just taking the derivative of the derivative. So that's going to be an easy one right there. And then I want to plug in that value as well, -3. We know it's going to be classified as a max or a possible min. I just want to see which one it is. So let's plug it in. And if we get that, we get -12. Let's go down here. -12 plus 1. That gives us -11. Okay. And because of the fact that we get -11 there, that -11 is less than 0, which makes this not a local minimum, but a local max. So I would say that there's a max at x is equal to -3. And two things had to occur. Here's my justification. Since my first derivative evaluated there was equal to 0, and my second derivative evaluated at that same spot was less than 0. So now we can classify as a maximum by the second derivative test, and I could say by second derivative test if I wanted to justify it using the name of the test that I use. Okay. So that's kind of how we use the second derivative, a little bit faster because of the calculation. We're getting a little bit faster at that. So we don't need that number line, we don't need to look at increasing, decreasing, we don't need test values. We can just simply do this process really quickly to figure out max min. So let's look at another example. It says use a second derivative test for different functions, and we're going to find all relative extrema for here. So we're not looking for a specific one, we're looking to classify all of them on this one. So the first thing I want to do is to get my critical values. So f prime, and I get 6x squared plus 6x minus 12. Okay, we set that equal to 0 and we start factoring, just like we did on Friday. We get that, that's factorable once more. That 6 is not going to matter because it doesn't have an x. So x plus 2, x minus 1. So x is -2 and x is 1. So the same process as before, figuring out the critical values, because this is where those maximum and minimums can occur. Next thing I'd want to do is to get my second derivative. My second derivative is pretty easy. We just get 12x plus 6. And then I can evaluate my critical values at that value, at -2. I plug it in. Here's my parentheses, sorry. We get -24 plus 6, which is -18. That's less than 0, therefore that's my max. It's kind of opposite. Negative value produces the max, positive value produces the min. Now I want to do that same thing with the other value. So 12 times 1 plus 6 and that's a positive 18 that's greater than 0, positive, so that's a maximum. So I can officially say that I have a max at x is equal to 1, since, and I have to have two things, since my f prime of 1 is equal to 0 and f double prime of 1 is greater. Sorry, that's not my max, that's my min. I don't know what I'm doing. It's too late at night. Sorry. Going back to that. Sorry, greater than 0 would make it a minimum by the second derivative test. I apologize. So this is a min. And because it's greater than 0. Positive values produce the minimum, negative values will produce the maximum. So I have a max at x is equal to -2, and again, two things. Since my f prime evaluated there is equal to 0, and the double prime evaluated there is less than 0. And both of these show that we're using the second derivative test to do that. So we can state the second derivative test, but we don't really need to because of the fact that we're using our second derivative in our justification. So that's kind of the second derivative test. So the second derivative allows us to figure out maxes and mins a little bit faster than our first derivative test did because we don't need the number line, we don't need test values. We can just get the critical values, take the second derivative really quickly and plug in. Okay, in addition to using the second derivative for identifying max and mins, we also use the second derivative to determine what we call the concavity of the graph. And the concavity of the graph, where it changes, is what we call a point of inflection. Okay, when we talk about concavity, we're talking about curvature. So the POI, the point of inflection, is the point where our curvature changes. Okay. And we can identify those points by doing the same thing we did for critical values. We wouldn't consider these to be critical values for f because they are a specific type of point now. And if we have a point of inflection, two things have to happen. The first thing is that our second derivative has to be equal to 0, or our second derivative is undefined, just like with a critical value, and our second derivative has to change signs. So much like a max or a min, there's only one type of point of inflection, so we don't care whether it changes from positive to negative or negative to positive. We only care of the fact that it changes signs. So when we talk about the curvature of a function, so if we have a function, and this is always my favorite function to draw, don't ask me why, it's just natural for me. The curvature, if we look at our curve is facing downwards, and then our curve is facing upwards. Okay. That point at which it changes from curving down to curving up, that right there is our point of inflection. And we use POI for abbreviation for short. Okay, so that's what we mean by the point of inflection of a graph. So not only can we use our derivative to figure out maxes and mins, increasing, decreasing, but we can also figure out the curvature and the point at which that changes, that point of inflection. Okay, and that's what we really use the second derivative for. So let's look at some graphs and talk about the actual the curvature. Okay, when we talk about curvature, it's called concavity of a graph. So when we're dealing with a parabola, if we think about that, when it's facing upward, we consider that to be concave up. Much like a cup. Concave up can look like a full parabola, like that, but it can also look partial, like our function, maybe our inverse exponential function, or our regular exponential function. Okay, so all three of those pieces are considered to be concave up. It doesn't have to complete a full U to be considered concave up. So, for example, our parent function for a cubic, like that. We have a piece that's concave up. That's this piece right here that looks much like that piece right there. Okay. If we have a parabola that's facing down, okay, we call that concave down. And that's concave down like a frown. Makes me sad. But concave down can look like an upside down U or the beginnings of an A, but it can also look the partials like our logarithmic function or our reflected logarithmic function can look like that as well. Just like with our cubic function below, that piece, that concave down, looks very much like that piece right there. Okay, so even though it's not completing the full U or the full A, we still consider it to be concave. Now, if we think about concave down, this part of the graph, I don't know why it turned red there, that was very weird, versus concave up, like that part of the graph right there. And then of course the point at which it's changing, that point right in the middle is our POI. Just like the graph here, that point is the POI. And the point at which we change from concave up to concave down or vice versa. Again, there's only one type of POI, so we don't care which way it's going. We just care that it's changing sign. So let's kind of look at a problem and look how we actually do this algebraically. Okay. If we're talking about concavity, we know that our graph is concave upward if our first derivative is increasing or our second derivative is positive. Okay, because you have to remember that our second derivative is the first derivative of the first derivative. I know that's weird to say and it's weird to think about, but we really have to start thinking about how all of these functions are kind of connected to each other. And we say that a graph is concave down if our first derivative is decreasing or our second derivative is negative. So we're going to concentrate algebraically on that piece right there and that piece right there to determine concavity right now. We'll wait until we start looking at just graphs in general and pulling information from graphs. Hopefully by Wednesday we'll start doing that. But if we think about just that piece right there, we can actually prove that algebraically exactly like we proved increasing and decreasing. So our second derivative can be used to find characteristics just like our first derivative. We do it the exact same way. We use the exact same process, number line and everything to determine those things. So let's kind of look at an example. It says, given the function f of x is equal to x to the fourth minus 4x cubed, identify any points of inflection and determine the concavity. So the first thing I want to do is to figure out where are my possible point of inflections, and that comes from the second derivative. We know we can't get to the second derivative without going to the first, so let's get our first derivative up there. These are pretty easy, polynomial functions. So there's our first derivative, and then our second derivative. That's one we care about here when we're talking about concavity. So 12x squared minus 24x. We're going to do the same thing, set it equal to 0, and just start factoring. So we can GCF of 12x, and we get x minus 2, which means x is equal to 0, and x is equal to 2. From here, these are my possible points of inflection. I still have to test them. I do the exact same thing. I use a number line to do that. So we're going to use a number line just like we did with maxes and mins increasing and decreasing. Of course, our number lines start at negative infinity, positive infinity. For this particular characteristic, we're going to use our second derivative to determine what's going on with f. So I'm going to put my values. These are points, so I'm going to use points on my number line, 2. And then to get some critical values, or not critical values, test values, I'm going to go with negative 1, 1, and 3. We're going to go and plug them into our second derivative to determine the sign. And again, I always plug into the factored form, which is that form right there. So if I take a -1 and I plug it in for 12x, I'm going to get a negative value. And if I plug it in for x minus 2, I'm also going to get a negative value. So a negative times a negative will give me a positive. If I take 1 and plug it in, I wind up getting a negative. And if I take a 3 and plug it in, I wind up getting a positive. Which means I have something that's concave up, that makes me happy. Positive people make me happy. Negative people make me sad. So concave down, and then concave up again. So again, that if we connect those 3 arches together, if I take those 3 arches and connect them, just like that, we actually get the shape of our graph, which is kind of nice. That, just like with the increasing and decreasing, that gives us the shape of our graph as well. Okay, so now let's actually answer the question and justify our answers. So first of all, I have POIs. So POI, that is an acceptable abbreviation, points of inflection at. If I look at 0, there's a sign change from left to right. And if I look at 2, sign change from left to right. So both of those are classified as POIs. So at x is equal to 0 and 2. And here's my justification. Since my second derivative changes signs, I don't care how it's changing. All I care about is the fact that they did change signs. There's only one type of POI, not like extrema that there's 2 types. I could say that this is concave up. Again, CU is a good abbreviation, acceptable abbreviation for concave up. On, because we're concave up on intervals, not at intervals. So on, I'm looking for positivity. So negative infinity to 0, and from 2 to positive infinity. And my justification always, since the second derivative is greater than 0. My second derivative being positive is concave up. Or concave down on 0 to 2. Since my second derivative is less than 0. And there we go. All of our information right there. Let's look at another one. Let me see how many more I got. 2 more. Okay. First thing I want to do is take my derivative. I get that. Second derivative, get 24x plus 42, set it equal to 0, and start factoring. So if I factor that, I'm only going to be able to take out a 6, a GCF of 6, so I get 4x plus 7, which means x is equal to negative 7/4. So I really only have one value to check. So here I am, my number line, only one value of negative 7/4. 0 is obviously a good test value. I'm going to go with negative 7, so I don't have to worry. Of course, negative 7 is going to be less than negative 7/4. Okay, so again, we're going to the derivative to plug in. So if I plug in, I'm going to go to the factored form right here. 6 is not going to make a difference because it's always positive. So it's really about the habits of 4x plus 7. If I plug in a negative 7, I'm going to get a negative value. If I plug in a 0, I get a positive value. So that makes negative 7/4 a POI. That's nice. So I have a POI. Ooh, that is ugly. Ignore that. That didn't happen. So I have a POI at x is equal to negative 7/4. Since my justifications are always the same. My second derivative, I can use f double prime of x. I can write f double prime. It doesn't matter. Since f double prime changes signs. Okay. I could say this is concave up on the interval negative 7/4 to infinity. f double prime is greater than 0, concave down on negative infinity to negative 7/4, since f double prime is less than 0. Okay, that is a comma up here, not a negative sign. That looked weird. So kind of the same process as we did on Friday, just using the second derivative instead of the first. Let's look at the very last question. It says the graph is of f, so this is the main function. This is f of x, shown below. State the signs of f prime and f double prime on the interval from 0 to 3. So for f prime, I want to look at, is my function increasing or decreasing? F prime is the slope of this. So since my function is decreasing, that means my f prime is less than 0, negative. Okay, and that's because f is decreasing. To determine f double prime, I want to look at the curvature. Now this is curved upward, so concave up. And because it's concave up, that means my second derivative is greater than 0. It's positive. That's because f is concave up. Okay. So once you finish this video, go ahead and put your phones back in the caddy, and I want you to try some of the practice on starting on page 100. Make sure you read the question so you don't overwork the problem. Just do what the problem is asking. Okay, if you have any questions, come see me on Tuesday morning. I will be back in class.